Good afternoon, everybody. I'm going to talk to you about a work that I performed during a sabbatical stay at Carnegie Mellon University several years ago. The subject is inkjetted arrays of gold-nanocluster chemiresistors for end-of-service life indicators in respiratory cartridges. The work was actually funded mostly by NIOSH, who also participated in the research actively, along with Gary Feder, which is the head of the ICES at Carnegie Mellon. All right. So, as an introduction, in 1998, OSHA recommended that all respirators be equipped with a NIOSH-certified end-of-service life indicator, ESLI, for the expectant contaminant, or if no actually exists, implement a cartridge change schedule to replace the cartridge prior to breakthrough. Actually, nowadays there's a very limited amount of indicators for carbon cartridges. They are only available for the very reactive gases, if you want. So the group at Carnegie Mellon, along with NIOSH, decided to attack the problem by inserting a miniature array of sensors inside the carbon filter, and then having some kind of an alarm when the carbon is exhausted. All right. Some words about chemistry and physics of carbon cartridges. Well, when an analyte is absorbed in the carbon actually saturates, and then the saturation front travels along the cartridge until it reaches a point which is called the critical layer, where there is an exponential decay in concentration. However, there's a finite concentration of analyte coming out of the carbon cartridge. At this point, the cartridge is no good anymore. And the trick is to find out when this happens before any analyte gets leaked into the mask. So you can, instead of monitoring the properties of the carbon, people normally try to monitor the concentration of chemicals in the carbon bed by assuming that when a sensor which is embedded inside will sense a chemical, that will mean that at least the upstream part of the carbon is saturated already. So you would like to put the ESLI somewhere before the critical layer, because then you will need to sense only saturation concentrations. If you put it too far away, you will have to reduce your limit of detection. Of course, you can put also the ESLI on the side. I'm sorry. You can put the ESLI on the side of the cartridge, so not to interfere with the flow of the air in the carbon. In that case, the concentration profile looks like this, and you have to put the indicator farther upstream. Now, in general, you may say that the indicator has to be small, has to be sensitive enough, has to discriminate between humidity and analytes, but also between groups of different analytes. It has to be insensitive to temperature changes. When a large concentration of material is absorbed in the carbon, the temperature rises, and you don't want the signal of the temperature rise to say anything about your cartridge. So, of course, it has to be robust and inexpensive. Well, a color changing indicator is a desired solution, but as I told you, there's only about 2 or 3 of them available. And a second best will be a temperature compensated miniature array of chemical sensors. And that's what we try to do. Okay, the array looks like this. Look at the center. We have a silicon chip about 2.5 millimeters across, which has 6 electrodes. 1, 2, 3, 4, 5, 6, arranged in a half-bridge structure. Okay, these are matched pairs. I mean, you put the same amount of chemiresistive material on this electrode and on this one. Now, the bottom ones get covered, so they are insulated from the chemicals, but they're exposed to temperature changes through the silicon and through the header underneath. So this will provide temperature compensation. Well, I should say right from upstart that this temperature compensation is never perfect. You always need an additional temperature sensing device, something like a meander of gold electrodes or anything else, in order to make the fine compensation of temperature. The electrodes themselves are circular, and they are specifically matched for inkjetting. Since this is a very small device and has many sensors on it, we thought that the best way to make it is through inkjetting directly on the electrodes. And since the inkjet produces round splats, the natural thing to do will be to use rectangular electrodes. This is IDT electrodes, interdigital transducers, because the resistivity of the material is quite high, and you need many electrodes in order to get a good measurement. So the structure is like this: the silicon chip with SiO2 on it, electrodes about gold titanium, and here we have the jetted splat on top of it, and the glass that covers underneath the bottom part. Delta V that you measure on the bridge is simply a measurement of the change of the resistance of your chemosensors. Now, the materials we were using for this is monolayer-protected gold nanoclusters. They were first synthesized in 1994 by Brust and Schifrin. In 1998 was the first demonstration of their use as chemical sensors by a group at NRL. I happened to be on sabbatical, exactly the same position at the time, so I was witness to their nascence, if you want. These are composite materials consisting of clusters of gold atoms surrounded by a single layer of organic molecule bound to the metal through a sulfur atom, mostly. They provide a naturally occurring and well-defined subpercolation state. The proximity between the conducting islands is controlled by the monolayer size. For example, if you have an octanthiol, like here, the shell size is about 0.6 nanometers, and the distance between the two islands is somewhere between 0.6 and 1.2, because sometimes they overlap. In any case, these small distances cause the materials, cause the electronics to tunnel. I mean, electrons can tunnel to these distances, and they can also hop between the islands, okay? The response basically is by swelling. When a material is absorbed in the nanoparticles, they swell. The distance between the islands, the conducting islands, is increasing, and therefore we get an increased resistance. Sometimes dielectric constant changes also affect, although in a smaller way, because when you have a high dielectric material, which is absorbed into the nanoparticles, it's much easier to separate charges from one to another, therefore the conductivity increases. Okay, these materials are soluble. You can dissolve them in many solvents according to the monolayer that actually surrounds the metal nanoparticle. Since they are soluble, you can also coat them using different methods: inkjetting, spraying, whatever, spinning. They exhibit extremely fast response time because, unlike polymers, the diffusion coefficient are very low. So these materials are very good for chemical sensing, and they have been since used in many occasions, even here in the Technion, I think. In any case, this is a demonstration of this material, which is insensitive entirely to H2O. However, it shows a large sensitivity towards toluene. Here I plot conductance against concentration. Okay, some words about inkjetting. Okay, the inkjetting of these materials were done on a home-built system, which is basically, it has the inkjet strobe and controller, okay, from microfab, and all the rest was built at the Robotics Institute at CMU. By the way, I've built a similar system in my institute many years ago, and then I'm building another one, a more sophisticated one right now. So it's really very easy to build. The system comprises of a vertical camera for positioning and a lateral camera for developing the inkjet process itself. Once you stabilize the process, you can load your ink and then jet it on a target, do the targeting, and inject on your device itself. Now, those two are leveled by the vertical camera at the maximum augmentation, if you wish, because the depth of field is very shallow, so you can make sure that everything is level. This is the actual picture of it. I won't say anything more about it. Now, the capabilities are as follows. For inkjetting water, the smallest droplet possible is something that has 14 picoliters. For organic materials, normally you can jet up to 45. Well, from 45 and up, depending on the nozzle. This is the nozzle we use of 30 micron diameter. Now there are nozzles up to about 100 diameters available. Okay, you can see various examples of jetting. This is our device here. This is jetted polythiophene. Actually, this whole project started with polythiophene. We jetted quite many of them and then discovered that they are probably good for OFETs, but they're not good for sensors because they drift. So we switched to the nanoparticles. Here is a coated, something that was coated by material we obtained from NRL. Here is another one, a phenylethyl, which forms a nice coffee ring. Here is a commercial material. And here I demonstrate the monolayer exchange capability of it. You can jet one nanoparticle here, and then you can squirt a tile on top of it and convert it to something else, which has a different property altogether. So you can make arrays of sensors not only by jetting the materials itself, but also by jetting reagents to change them. And in the middle, we see another use of our inkjet. This is actually, when we jet a drop of regular polymer in here, the polymer gets sucked up into the narrow channel, which is about 1 to 2 micron wide, and there's no other way to coat these narrow troughs except for this method. Okay. A few more slides about jetting. On the left side, we can see wet drops and the dry splats produced by 1 drop, 4, 8, 16, and 20. Well, basically, the physics of this is that the size of the wet splats is controlled only by the volume of the ink and by the contact angle. Sorry. And by the contact angle, okay? So, by putting more drops, you simply increase the diameter, the DF. Here I can show you a nice film, I hope, of a drying drop. Okay, next. When we put more salt, when the volume of the drop is larger than necessary to cover the whole area, the wet splat actually extends beyond the electrodes and goes also to the silicon dioxide, but then it contracts and covers the electrode, forming a coffee ring. On the left side, you can see a coffee ring effect, and on the bottom part, you can see the actual structure. Now, if you tilate your surface before inkjetting, you can increase your contact angle, so the same volume or even bigger makes a smaller splat. Again, you can see the very nicely the coffee ring effect. Please notice that the coffee rings have some pinholes along the perimeter of the electrode themselves. I'll never get used to it. Okay, look. Okay, these pinholes here are exactly here at the edge of the electrode, and the same was here, and the same was here. Okay, here you can see two lines, and here is one line, and the second one is, I'm not sure if it's a true line of pinholes or not. However, this gets to show you that the jetting has some unique morphology that may be influencing your performance. Okay, here are some preliminary studies. When we jet 10, 20, 30 drops and generate perfectly matched pairs, okay, and you can see the response to toluene basically needs a certain amount of material before you start to get a nice response. If it's too thin, you get mostly noise. Okay, here's the demonstration of the temperature dependence of the system. We increase the temperature, but the signal remains flat. And on the bottom part, you can see some signals after exposure to different solvents. Okay, so all three bridges act very nicely. So what we did next, we packaged it in a TO5 with a filter, inserted in a carbon bed, and tried to see how they perform. And actually, what we saw is that the yellow line is a breakthrough. This is a GC line inserted into the carbon bed, monitoring the actual concentration. And the pink line is the response of one of the sensors. And you can see very nicely, you can follow easily the breakthrough through the carbon. So at this stage, we inserted those devices into several cartridges in different configuration, send them to the manufacturers in order for them to fill the carbon so we could test it. I won't talk about it anymore, but rather in the few minutes that were left, I want to share with you some findings that we had when you try to see if there are any scaling effects of the electrodes. Okay, so what we did is we made a chip which has 18 transducers in it with different gaps, okay? I'm sorry. Okay, these are 3 micron gaps, 4 microns, 6, 9, and 12, 2 rows. There's also a meander temperature sensor right here. We jetted on top of it either 12 or 24 or 18 or 36. So in one chip, which of size of 2.5 by 5 millimeters, we can make an array of 18 sensors, which is remarkable, I think. This is how actually these jetted devices look like. Okay, it's almost perfect jetting. Well, not always, but most of the time. This is the setup that we use to monitor them. This is an actual PC board that they made me to make because I was in an electrical engineering department. So no student volunteer, so I had to design a PC board. That's my first and the only PC board ever I designed. Anyway, temperature response don't show any gap effect, a very small one. Toluene response also doesn't show any special gap effect. Now, look at the beginning. When the films are very thin, you cannot measure the resistance on the wider gaps because resistance is higher than 120 megaohms, which is the limit of the instrument we were using. However, when you increase your thickness, you can see a very nice response, and there's no basic difference between them. The same is true about isopropanol. I won't talk about it later. However, when we expose it to water in a very slow way, we increase the concentration, the humidity, from about 30% to about 90%. What happens is there's a huge gap effect of the electrodes, okay? And it starts at about 60% of relative humidity. Okay, I'll show you later. This actually looks like this. You see, from 60% up, there's a big difference of the response at high humidities. Now, what's causing all this? We felt that this has to do something with the water that is absorbed either on the electrodes or on the SiO2 underneath or in the film itself. Well, people have shown by studying FTIR that silicon dioxide above 60% of humidity, actually first of all, there's an ice-like water, about 4 monolayers that is formed. However, from 60% up, there's free water, actually up to something like 7 or 10 monolayers of water. That much water at high humidities can do many things, and I'll show you in a minute. So we felt somehow that this is related to water. Also, people studying polymers, either hydrophilic or hydrophobic, have found that water is absorbing underneath the polymers at very high humidities. So, if we look about the formalistic view of the sensors, if you take any resistor, okay, you can quickly develop that the response is delta R over R actually is entirely geometry independent. If you have a resistor measuring 2 points, no matter what you measure, how it looks like, the change will not reflect the geometry at all. However, if you introduce contact resistance, then only then you can see some effect of gap. However, the gap effect will be larger when there's a large contact resistance sensitivity. Now, we didn't see the sensitivity to toluene, but I believe we saw it towards water. Somehow the contact resistance changes very much when it's exposed to large amounts of water. Now, I can explain phenomenology way. Okay. If water is absorbed in the nanoparticles itself, it simply changes the resistivity. This shouldn't reflect any gap effect. The same thing if the water is absorbed underneath, you get simply a parallel path of conductance. So the resistance should go down. However, if the water is absorbed on the electrodes themselves and somehow causes the shift, causes the resistance to increase, you will get an increased resistance. So, in order to eliminate, 3 minutes, in order to eliminate the effect of the SiO2, we actually treated it with HMDS, okay, by eliminating the parallel path. And what we saw, this was before, and this was after. Okay, all the negative effect of all the electrodes of the sensing disappeared, and everything now goes up. Because probably this is the intrinsic response and the contact response also. I know it's a bit difficult, but I hope I can convey this picture. Now, in this case, what we did is we covered the electrodes with octantile in order to make them hydrophobic to repel water, and then to look what happens. So the idea was as follows. I'm sorry. if this is the pristine situation when you have your nanoparticle and the gold, at high humidity, you can get water absorbed on the electrode or on the SiO2. When it's absorbed on the electrode, you get increase in resistance, and on the SiO2, you get decrease, and a strong gap effect in this case. However, if it's dilated, there's no water that can get very close, and therefore the only water that will be absorbed will be on the SiO2, and therefore you'll get a decrease in resistance. And indeed, this was the case that we saw for the 3 and 4. You see a decrease in 40% of resistivity upon dilating the electrodes. So basically, water is a big problem for sensing, and you have to treat your surfaces very well in order to control your... sorry. Okay, just one more thing. All right, if we plot the difference between the 3 micron gap and 12 micron gap, we get this kind of transfer function between humidity and signal. So we thought that this can be utilized to make a novel humidity sensor. And it goes like this. The normal humidity sensors is in the upper picture. It's an array where you have 3 different coatings, and you get some kind of fingerprint effect. And if one of them is sensitive only to RH, you can monitor your relative humidity very easily. The one that I'm suggesting, according by this work, is actually to leave this one uncovered, okay, but make it with different electrodes, one with a 3 micron gap and one with a 9 micron gap. When this sensor will encounter a solvent, both of them will respond in the same way because there is no gap effect. However, if they will encounter relative humidity at high humidity, this will respond. And what we did, we took the system and subjected it to 500 ppm pulses of toluene, 2 minutes on, 2 minutes off, while changing the relative humidity. Okay? And what we got is that, okay, here is the response of the 3 micron sensor. This one. This one is the response of this is the humidity change. And this line in here is the response of the sensor. Look here, when the humidity doesn't change much, you barely see any toluene response. Same thing here, which means that this sensor can act very nicely as a humidity sensor, even at very high concentrations of other solvents. And this is the transfer function. When we plot when we plot this against this, we get the transfer function, which is exactly the same as it was before, which means that the sensor works perfectly. Okay. I don't think I have any time left, so I just conclude. Okay, inkjetted chemiresistor array for ESLI was demonstrated. Well, not entirely. We made some progress towards it. Advantages of inkjetting of chemiresistor arrays were discussed. A parametric study revealed an unreported gap width dependence sensitivity to RH at relative humidities higher than 60%. A novel humidity sensor with no solvent cross-selectivity was demonstrated. Its implementation relies on the ability to stabilize interfaces. Okay, let's go to the acknowledgements. I want to acknowledge the team at NIOSH, Ron Schaefer, Tony Rossi, and David Barkand. The team at Carnegie Mellon, David Lambert from electrical engineering, Weiss from the Robotic Institutes, and some graduate students. Funded for this work was provided by the US Air Force Scientific Research and the National Institute of Occupational Safety and Health. And some of it was provided by the National Research Council, which actually funded my salary when I was there. So I want to thank you for your attention.